Thank you very much. Thanks. It's an honor to be here. Thank you very much for the invitation. So I would like to talk about holomorphic disks and knot invariants. And in particular, I'd like to describe not Floer homology. Okay. Not Floer homology is an invariant for knots, which is defined using holomorphic disk techniques. And I'd like to describe what it is, what it's good for, where it comes from, and then how one should think about it. So not Floer homology is an invariant which associates to a knot. So not Floer homology, the version that I'm going to describe right now, this is an invariant which was defined in joint work with Zoltan Subel. The construction I'll describe was also independently discovered by Jake Rasmussen. And the invariant associates to a knot in the three-sphere, though there are generalizations to null homologous knots in an arbitrary three-manifold, but that's the sort of thing one's not interested in a public lecture. And it associates to a knot in the three-sphere, a bigraded abelian group. And I'm going to notate it, I'm going to write it as HFK hat of K. And so it's bigraded, which means that it's indexed by a pair of integers. D and S are integers. So there's the knot Floer. One in algebraic topology, one studies homology groups, which are graded by natural numbers. And this is a theory which is graded by a pair of integers. So the way to think about it pictorially is to imagine the plane, z plus z. And over each lattice point in the plane, we have some finite group, finite abelian group, sorry, finitely generated abelian group. And generically, over the generic lattice point, one actually has the trivial group 0. So I suppose I should say this group here is actually finitely generated. Which means, of course, that there are only it has finite support for finitely many D and S. This group is non-trivial. Outside of some region in the plane, the group is trivial. And it has one way to think of. So this. Okay, so we're trying to understand some object. Well, something that's rather simpler to understand is its Euler characteristic, and this group has the property that if you take the Euler characteristic in the vertical direction, then you obtain some coefficient of the Alexander polynomial. Or more, in fact, what you get is that if you think of the graded Euler characteristic of this group, one gets the Alexander polynomial, which is to say that if we take the alternating sum of -1 to the d times the rank of HFK dks times t to the s, and we sum over d and s. This object right here is this familiar Alexander polynomial of the knot. It's an old familiar creature. So maybe I should, so this is the nature of the invariant I'd like to describe. Maybe I'll just draw some examples for concreteness. Draw to exactly opposite example to what I wanted to draw. Here's the right-handed trefoil knot. Its Floer homology is a z, and a z. So this is the s and this is the d. So at s equals 1 and d equals 0, you have a z. At s equals -1 and d equals, sorry, at s equals 0 and d equals, well, right here you have a z and right here you have a z. And everywhere else you get zeros. Another example is the 3-4 torus knot, where we draw this grid. And we run out of space. I actually drew a correct picture. I'm not sure it's visible. Ah. All right. This is the 3-4 torus now. Floer homology 3-4 torus. Okay. Well, anyway, we get the plane, and it's decorated by these groups. And one thing one can ask is what kind of. So the first question I'd like to describe, rather than what its definition is, which I'll save for a little bit later, I'd like to describe some of the things that it's good for. So we have these groups. What do they measure? So does this slide in some way? Modern technology. Okay, great. So so let me describe, before I describe the definition, let me describe some applications of this. So the first point that about this group is that it detects the unknown. Which is to say that if you have any knot, and you know that its knot Floer homology is isomorphic to the knot Floer homology of the unknot, then in fact, K is the unknot. And in fact, there's a stronger version of this result, which is that it detects the genus of the knot. Let me just recall. If you have a knot in the 3-sphere, then that knot can be thought of as the boundary of an oriented surface called a Seifert surface. So for example, for the trefoil, one can construct 2 sheets of paper and glue them together by strips, and in this way we have an oriented surface whose boundary is the knot. And it's an interesting measure of the knot's complexity. So that, of course, there are many different Seifert surfaces for a knot. You can always add a handle and get then a surface of larger genus. But it's an interesting measure of complexity of a knot to find the minimal genus of any Seifert surface of a knot. That's called the Seifert genus of a knot. And it's a kind of solid way of measuring how complex the knot is, in the sense that the Seifert genus of a knot is 0 if and only if the knot is the unknot. And so this is a classical numerical invariant of a knot. And so Seifert genus. And let me just write out the definition. This is the minimum genus of any surface embedded in the 3-sphere whose boundary is equal to our knot. And in fact, knot Floer homology detects a Seifert genus. And how does it detect the Seifert genus? Well, we have this blob of abelian groups supported on the plane. And the Seifert genus, in fact, is just the breadth of this, or a function of the breadth of this. More specifically, the length of this side is the Seifert genus. Or said differently, the theorem here is, and this is a theorem that we proved with Zoltan, the theorem around 2003. The theorem is that the Seifert genus of the knot is equal to the maximum of all integers S such that the knot Floer homology group K S is non-trivial. Okay. So this is a theorem that we proved with Zoltan, but I should probably admit that it's actually sitting on top of a rather large edifice of mathematics developed by a number of other people, including Gabay, Thurston, Ellie Ashberg, and Donaldson. And in fact, this whole philosophy is very much based on work of Kronheimer and Mrówka. In gauge theory. their working gauge theory. Okay, so this is one application of this invariant. Let me describe some other applications before I move on to where it comes from. I'll just release this. Second is that it's closely related to a three-manifold invariant. And that three-manifold invariant is what we call Hegar's Floer homology. But the point I should just make is that given the not Floer homology groups of a knot, given a knot in the three-sphere, there's a way of constructing a new three-manifold called Dane surgery. Dane surgery is the operation where one takes a regular neighborhood of a knot, which is a solid torus, and deletes it from the three-sphere, and then glues it in differently. The manner in which one glues it in is specified by a rational number. So that is to say, given a knot and a rational number, one obtains a new three-manifold. And the theorem is that given the principle is that given a knot and a rational number, P over Q, if one knows the not Floer homology of that knot, one can extract from it a three-manifold invariant which depends only on the P over Q surgery on the knot. So I don't want to state this carefully. I want to state a consequence of it instead. And the consequence says that if you know that you have a knot in the three-sphere and some surgery on it is specially constrained, then that puts constraints on the not Floer homology. So more specifically, here's a theorem, again, me and Zoltan, which says that if K is a knot in the three-sphere and P over Q surgery on K is a length space LPQ prime, then the not Floer homology is heavily constrained. Let me, rather than giving the full statement, say one of the consequences, and that is that the rank of the not Floer homology Ks is always less than or equal to 1. So let me just say this in terms of our picture here. So we have our blob on the plane. We have our abelian groups, which are indexed by points in the plane. The statement is that for any vertical line, the groups are either all 0 or a bunch of zeros in a single z. So this, if you combine this with the statement about the Alexander polynomial, also says that if a knot has a length space surgery, then its Alexander polynomial has all the absolute values of its coefficients are less than or equal to 1. But this is a type of constraint that comes from not Floer homology. The third application I'd like to give before I move on is wow, we have all these blackboards. That not Floer homology detects whether or not a knot is fibered. So this is a theorem proved. Okay, so let me just first say that a knot is fibered if the knot complement admits a map to the circle. So the knot complement always admits a map to the circle, but what we want is a special type of map to the circle, which is a fiber bundle. So we want the Seifert surfaces. We want basically a one-parameter family of Seifert surfaces with the same genus that sweep out the entire three-sphere. That's the definition of a fibered knot. And there's a classical theorem, the Alexander polynomial, which states that if a knot is fibered, then its Alexander polynomial is monic. The outermost coefficient is plus or minus 1. And there's an analogous theorem that we proved with Zoltan, which says that if you have a knot that's fibered, then its outermost knot Floer homology group is actually one-dimensional. And there's a remarkable converse to this, which was proved by, by Gigini when the genus of the knot is 1, and Yini when the genus is bigger than 1. And they say that, that if K has genus G, then if the knot Floer homology group in that G value of S is one-dimensional, this is true if and only if K is fibered. So maybe I should remember one direction of this is not so hard, and that was actually we did with Zoltan, and the other direction, kind of amazing, was done by Gigini and Nini. Okay, so a quick corollary of these two theorems together is that if you have a knot in the three-sphere which has a length space surgery, then it must be a fibered knot. Okay, so these are some of the applications of knot Floer homology. There are also some applications to Legendrian knots, which I thought I would talk about if I have time, but that seems increasingly unlikely. So let's just leave it at that. Okay, so let me say now a little bit about where these groups come from, and then I'll give a definition, and then I'll give at least one definition. So what I would like to describe are some recent computational advances in this theory. So, but before I do that, maybe I should give some more of the background. Okay, so where does knot Floer homology come from? So maybe I should go back to my graduate student days. So in the late 80s, there was a revolution in four-dimensional topology, which was gotten by the introduction of equations from mathematical physics to be used as tools to study smooth four-dimensional manifolds. So this was done by Donaldson, pioneered by Donaldson, and then Taubes, Holomorphic, and others. But the tool here was to associate to a four-dimensional manifold. One started with a smooth four-dimensional manifold, equipped it with a metric, and then considered the moduli spaces of some PDEs, which could be associated to the four manifold with the metric and some additional data, which I'm now going to suppress from this talk. So the point is that one has a moduli space of solutions to some PDE, which the physicists are good enough to hand to us. And from that moduli space, one extracts some numerical data. Maybe that moduli space is zero-dimensional. One just counts the number of points with sign. Maybe it's a big dimensional manifold, but there are some canonical cohomology classes, and one cuts down by those. So the point is that from one chooses the metric, one looks at moduli spaces of PDEs, one performs some algebraic topology magic to that moduli space and gets out numbers. And these numbers, it turns out, are independent of the original choice of metric. These were the Donaldson invariants of the four manifold. And along with Donaldson invariants came, is it okay if I write here? Can everyone see it? Yeah? Okay. So along with these invariants for four manifolds comes an invariant called instanton Floer homology. Instanton Floer homology was an invariant for 3 manifolds. It still is an invariant for 3 manifolds, which fits into Donaldson theory in the sense that if one has a group which is a graded abelian group, or Z mod A graded abelian group associated to 3 manifold with additional topological restrictions, which I will not go into, and if one has a 4 manifold with boundary that 3 manifold, then there's a natural generalization of Donaldson's invariant to a relative invariant, which takes values in that Floer homology. So there's a relative Donaldson invariant, which lives in the Floer homology of that 3 manifold. And why is this useful if one starts from 4 manifolds? Well, if one has a 4 manifold which is composed of a pair of pieces which are glued together along a 3 manifold, then the statement is that the Donaldson invariant of this 4 manifold, this glued together 4 manifold, is gotten by pairing the relative invariant of one side with the relative invariant of the other side inside the Floer homology of that 3 manifold. So this was the general picture. Only parts of this general picture have been worked out to date, but this was certainly the guiding philosophy. In around 94, the situation in smooth 4-dimensional topology took a rapid change with the introduction of the equations of Seiberg and Witten. Physicists who introduced a new PDE one could consider to extract numerical invariants out of smooth 4 manifolds. And these are called the Seiberg-Witten invariants. They're obtained in much the same picture, much the same means that the 4-dimensional invariants are extracted. And in a similar way, one could associate to a 3 manifold with boundary some given 4 manifold a version of a Floer homology. Well, there are actually several variants of this. I'll just be vague and write HM. This is the monopole Floer homology of that 3 manifold. Whose complete definition was given only very recently by Kronheimer and Ruvka, which fits into a very similar footing. So everything I said over here works with the sort of global search and replace of Donaldson by Seiberg and Witten and so forth. So this is a picture where one associates to a 3 manifold an abelian group, and to a 4 manifold with boundary and a vector in that abelian group, and to a pair of 4 manifolds with boundaries y, a pair of vectors which can be paired to give an invariant of the closed 4 manifold. So Heegaard-Floer homology grew out of our attempts at trying to understand these invariants from a much more concrete computational point of view. For a topologist to say the way we're going to study a smooth 4 manifold is to equip it with a PDE, which the physicists tell us, and then we solve some PDE on it, and then we do algebraic topology, and then we get a low-dimensional invariant. That's a little bit unsatisfying. For topologists, we like to pull apart spaces and understand them concretely and say very, very explicitly what it is that we're trying to measure from a topological point of view. So Heegaard-Floer homology arose out of my efforts with Zoltan to understand the geometry behind Seiberg-Witten theory from a concrete combinatorial point of view. So far, that dream has not yet been realized, but we seem much closer than we were when we began. So let me say a little more here. So Heegaard-Floer homology defined in Zoltan around 2000 started from, it's an invariant, one starts from an invariant for 3 manifolds, and I'll explain a little bit about its construction, but not much. And it fits into the same general scheme, which is to say that one can also construct a 4 manifold invariant, which conjecturally is isomorphic to Seiberg-Witten theory. But let me say a few words about the construction of Hegardt-Floer homology in general, and then I'll move back to not Floer homology. So the construction of Hegardt-Floer homology comes as follows. So we want to start with the three-dimensional manifold. Sorry, I should actually backtrack. So this version of instanton Floer homology was actually the second Floer homology group defined by Floer. These constructions were his idea. Floer homology in general is an attempt at understanding Morse theory for infinite dimensional manifolds. And instanton Floer homology that I've said over there is one instance of that, Floer homology for Morse homology for infinite dimensional manifolds. Another one was his original one. His original one was an invariant for symplectic manifolds equipped with, so a symplectic manifold is a 2n-dimensional manifold equipped with a closed 2 form whose top exterior product is nowhere 0. This is a symplectic manifold. A Lagrangian submanifold of a symplectic manifold is an n-dimensional submanifold with the property that the restriction of the symplectic form to it is identically 0. So the largest dimensional submanifold for which that can happen. And Floer's original construction was Lagrangian Floer homology. Was a theory which is associated to a symplectic manifold equipped with a pair of Lagrangians. And it associates to them a graded abelian group whose Euler characteristic is the algebraic intersection number of these two Lagrangians. But that's the Euler characteristic of this group. There's a refined obstruction to pulling those two symplectic manifolds apart. This is Lagrangian Floer homology. I should say maybe one word about it. It's impossible to do justice to it in the amount of time that I'm trying to, but so with apologies. It's defined by a chain complex whose generators are, let me work with Z mod 2 coefficients. They're generated by intersection points between the two Lagrangians. Just as in classical Morse theory, the generators of the Morse complex are critical points of a functional. And the differentials in this complex count holomorphic disks. So we have a pair of Lagrangians, L0 and L1. The y component of the differential of x is the number of pseudo-holomorphic disks which look like this. They're Whitney disks. So the left arc lives in L0, the right arc lives in L1. We divide out by translation. There's a rather longer mantra here, but I'm going to sort of skip it. So let me get to the point, which is that in Hegardt-Floer homology, the construction we wanted was to tap in, so to extract from a three-manifold a setting to which we can apply this picture. That is to say, if one starts with a three-manifold Y, such a three-manifold can be described by what's called a Hegardt diagram. A Hegardt diagram, let me just say this a little slower. So first of all, a handle body is the three-dimensional manifold you draw on the blackboard every time you draw a Riemann surface. So actually, you're drawing a surface, but you also think about the interior of that surface. That gives you a three-manifold with boundary. And unless you're perverse, every time you draw this, you're actually drawing a handle body. So this is a handle body. And so there's a theorem, standard theorem in three-manifold topology, that if you have any closed-oriented three-manifold, then it can be written as a union of two handle bodies glued along their boundary sigma. And what specifies a handle body? Well, a handle body is specified by a G-tuple of curves, which bound G-tuple of curves living inside on sigma. So sigma here is a surface of genus G, and we're choosing G curves which live on sigma. And those G curves have the property that each of them bounds a disk inside of the handle body, and they're all homologically linearly independent. So that is to say, let me just say it again. A handle body with boundary sigma is specified by a G-tuple of curves which are homologically linearly independent and which are disjoint. And they're connected to the surface by the property that each of those curves bounds disks inside of that handle body. So that is to say, a 3-manifold can be described quite combinatorially by an oriented 2-manifold sigma and a pair of G tuples of curves, alpha 1 to alpha G, beta 1 through beta G. And the construction of Heegard-Floer homology is an instance of Lagrangian Floer homology where we have to associate to a 3-manifold now some kind of symplectic situation. That is to say, we have a 3-manifold with a Heegard splitting. Let's associate to that a symplectic manifold. So the symplectic manifold we will associate to it is the G-fold symmetric product of sigma. That is to say, the set of unordered G tuples of points on sigma. So in this case, genus is 3. So we're looking at the space of triples of points on sigma. And they can come together, and it turns out that this miraculously is a smooth algebraic surface. A smooth algebraic variety, and in particular, it's also a symplectic manifold. Not only that, but it's equipped with a pair of obvious half-dimensional subspaces, which are those G tuples of points where one point is asked to lie on each of these alpha circles. That's one of the half-dimensional subspaces. So I look at triples of points where one lives on each of these alpha circles. That I'll call T alpha. And there's another analogous, so we're specifying a closed 3-manifold, then we needed a pair of G tuples of circles. So that gives us another Lagrangian submanifold, T beta, another half-dimensional submanifold. And to make this construction actually work, we needed to also choose a reference point Z outside of the alpha and the beta circles. And we look at essentially the Floer homology of the G-fold symmetric product of sigma relative to this pair of Lagrangians. Except there's a technical point, which is that we don't want to count holomorphic curves that cross this Z. So if you like, it's as if we were working in the G-fold symmetric product of the punctured surface. And this group is the Heegard-Floer homology of our 3-manifold. So one of our first theorems is that that's actually a topological invariant. There are a number of choices that went into the construction, but what you end up with is actually a topological invariant of the 3-manifold. Now, I've been talking about not-Floer homology. Not-Floer homology is a small generalization of this picture where one chooses not one but a pair of base points. So let me just make this observation that a Heegard diagram together with a pair of reference points actually specifies not just a 3-manifold, but a knot inside of that 3-manifold. How do we get the knot? Well, we connect the real picture should be somewhat more complicated. Here's my W, here's my Z. And if we delete all the alpha circles, we end up with a connected surface. So that's to say, you can go ahead and connect W to Z while crossing only beta circles. Similarly, you can connect W to Z crossing only alpha circles. So we can actually construct the following closed curve on sigma, which has two arcs. It goes from one goes from W to Z, crossing only blue circles. One goes from Z to W, crossing only red circles. And then, if you think about the Heegard diagram as a splitting of your 3-manifold, we take one of those arcs and push it into one of the handle bodies, and the other one push it to the other handle body. That way we get a closed knot inside of our 3-manifold. And not-Floer homology actually is simply the same construction, except now we puncture in Z and W. OK, so I've probably not given enough details here for the non-experts to go and reconstruct the definition of not-Floer homology. But I wanted to give a quick flavor of what the theory looks like. So let me just sort of get to the point here that I want to make, and that is that this is a chain complex whose generators are completely combinatorial. They depend only on the topology of the underlying picture, but their differentials count holomorphic curves in the G-fold symmetric product of sigma, and therefore they're not topological at all. So it remained a very interesting challenge to try to actually come up with a combinatorial method of computing these things. And today, today we have three such approaches. So combinatorial approaches to computing. So there are two of these there's a method of Sharkar and Wang, Shucharit Sharkar and Judge and Wang. And their approach was to start with an arbitrary Hegar diagram for a knot and then complicate it very much. So that at the end of the day, at least one of these versions of knot Floer homology can be computed combinatorially. The differentials in that chain complex are only combinatorial. So, so start from an arbitrary Hegar diagram. For K, and then spoil it or fix it depending on your perspective. But what makes it, the algorithm makes the diagram much more complicated. So we complicate the diagram so that the differential becomes a completely combinatorial. So this is one approach. Another approach. So this is from summer '06. Another approach, also from summer '06, was joint work with Ciprian Manolescu, myself, and Sharkar. And this is to start not from an arbitrary Hegar diagram for a knot, but from a very special type of Hegar diagram for a knot called a grid diagram. And for the grid diagram, the advantage is that one can write down a differential which computes any of the versions of knot Floer homology. But unfortunately, the diagram is, again, just as the Sharkar-Wang algorithm, it actually has many generators. So we end up with a huge chain complex. So if you have an n-crossing knot, then you have a chain complex with roughly n factorial generators. And you compute its differential, and you end up with these knot Floer homology groups. And there's a third approach which maybe maybe I should say that this approach was developed further also by Manolescu, myself, Zoltan, and also Dylan Thurston. To define for grid diagrams an invariant which is in fact isomorphic to knot Floer homology by this earlier theorem, but in fact we were able to give a complete self-contained proof that this is actually a knot invariant. So, this approach has been developed a bit more since the first paper, but I'd like to describe a third approach, which I guess is from spring '07. And this is a third approach to understanding knot Floer homology. And if I've so far said nothing which was concrete enough to follow, I promise now I will. So I'll actually give a completely explicit description of knot Floer homology from this point of view. This point of view is to start from a generalization. Knot Floer homology. We start by generalizing knot Floer homology to singular knots. This generalization was due to András Stipschitz, Zoltán Szabó, myself. And then to use this to construct a cube of resolutions picture. To calculate. Not for homology. And this again was working with Zoltán and myself. Okay. So let me try to just describe this completely and put it into some context. So so let me start by putting it into context. So there's a method for computing the Alexander polynomial, which involves throwing away the definition and just looking at the so-called Skene relation that it satisfies. The Skene relation says that the Alexander polynomial of a knot is, the Alexander polynomial of a knot with a certain type of crossing minus the Alexander polynomial of a knot with the opposite type of crossing is equal to t to the half minus t to the minus a half times the Alexander polynomial of the link you get by resolving the crossing. So let me write that Skene relation in maybe a slightly unfamiliar manner, which is to say that there's an invariant of, if you have a knot with some crossing in it, you can do the following things to that crossing. You could, of course, leave it alone. You could singularize it so that you don't have a knot anymore, but you have a knot with a double point in it. You could resolve it, or you could change its type. So the Skene relation I'd like to write is, to consider the knot with the so-called positive crossing. Well, its Alexander polynomial is equal to the Alexander polynomial of this singular knot plus t to the 1/2 times the Alexander polynomial of the resolution. And there's another variant where we write t to the minus 1/2 times the Alexander polynomial of the resolution. If you like, you could take this to be the definition of the Alexander polynomial of the singular knot. Alexander polynomial of the singular knot, you can decrease the number of singular points by either positive crossingifying them or resolving them. And if you take the difference of these two relations, you get the more familiar Skene relation for the Alexander polynomial. And what we'd like to do is we would like to, one of the philosophies, this was actually the philosophy that upon which Kovanov's beautiful, so I should mention that Kovanov also has a bigraded abelian group, it's a bigraded group whose Euler characteristic is the Jones polynomial. And in fact, with Kovanov and Rozansky, have a version where the Euler characteristic is the SLN polynomial, and in fact, they have another version whose Euler characteristic is the Humphrey polynomial. So their basic philosophy was that a Skene relation among among polynomial invariants should correspond to a long exact sequence of homology invariants, and using that idea, they were able to actually define invariants with these properties. So we're going to adopt a very similar approach for not-Floer homology. We look at these two Skene sequences, and we want to use them as building blocks for a theory. So, so with that said, let me back off now from the general case and define just a group associated to a completely singular knot. And that's going to be defined by the following construction. So consider a singular knot. So this means we take a knot projection and we just take the honest projection of the knot. We don't remember anymore which are over and which are under crossings. And I want this projection to be of a special form, which is to say I want it to be in braid form. So that's to say I imagine there's that half of that picture looks like what's called a braid. And well, I want this to look like a braid, and I will close up that braid on the other side. So for a knot in this special form, I also pick one other piece of data, which is I distinguish one of the leftmost edges. And now, what I'd like to do is I'd like to associate to this picture a ring. And the ring is the following ring. Each edge in this picture, I number each of the edges in this picture. So 1, 2, 3, 4, 5. And I view my star as subdividing this into two pieces. So the star subdivides the singular picture, and then we have all the other edges which we number. And what I'd like to do is I'd like to consider the polynomial algebra, and let's work with Z2 coefficients just for sanity. And we take variables, one corresponding to each edge. And in fact, I'd like to look at an even more slightly horrible ring, which is I want to introduce yet one more indeterminate t, and then I want to complete, I want to allow myself to invert t, and then I want to complete with respect to t. So these are infinite power series in t, and they have finitely many t inverse terms in them. This is my underlying ring. And at each singular point, each singular point corresponds to a relation. So at each singular point, I've got two outgoing edges, A, B, and two incoming edges, C and D. And I'd like to introduce the relation UA, UB equals UC, UD. In fact, I'm going to put a t squared out in front of the UA, UB. So we've got t squared UA, UB equals UC, UD. And I'm also going to consider the relation t times UA plus t times UB equals UC plus UD. And these are relations that I want to divide out my ring by. They're not all the relations I want to divide out my ring by. I'm going to generalize this relation a bit more. And the way we generalize it is the following. Let W be any subset of singular points of our diagram. So here's W, some set of singular points. It has some number of outgoing edges, and it has some number of incoming edges. So the generalization of this relation, then, is that the product of all the outgoing edges is equal to the product of all the incoming edges times t to the total weight. So if my set W has n points in it, I look at t to the 2n, actually. So each of these, each singular point counts with weight 2. So, so these are the relations we divide this ring out by. And I promise I'll make it. And it might have seemed a little bit artificial that each object has weight 2, but that shouldn't be so artificial because, in fact, if you have a crossing in your picture, there are two things you can do. One is that you can singularize it to get this singular link. Another thing you can do is you can resolve it. And I could say that we resolve it and have no distinguished points on those resolution points. That's one perfectly consistent thing to say. But another thing to say would be to imagine that this double-weighted singular point splits into two. So we've got two single-weighted singular points over here. And the relation that we now have is that t times UA is equal to UC. And t times UB equals UD. So this is the way we're going to view our smoothings. So again, you can just imagine either eliminating one of these two variables from this picture, but for some reason I'll prefer not to, which will be clear in a moment. Okay, so I've now described the algebra associated to a singular knot. The algebra associated to a singular knot is just this ring divided out by all of those relations. Maybe I should just observe that if S is a disconnected singular knot, this algebra is trivial, because that means that you have some collection of vertices which have no outgoing edges and no incoming edges. So the relation you end up with is that t to the w equals 1. And since we're working over a Novikov ring, you can invert 1 minus t to the w and you get the 0 ring. So that's just a little observation. Okay, and now what we'd like to do is we would like to form what's called the cube of resolutions. So, sorry, I've now described the invariant of a singular knot. What I want to now describe are the invariants associated to an arbitrary knot. So if you give me an arbitrary knot, then we're going to associate to that arbitrary knot what's called this cube of resolutions, which is to say, if it's an n-crossing knot, there are 2 to the n different singular knots you can associate, where if that crossing is a positive crossing, then we associate to it we say that its 0 resolution is this singularization, and its 1 resolution is this smoothing. Whereas if it's a negative crossing, we say that its associated 0 resolution is the smoothing, and its 1 resolution is the singularization. So we have this notation. So at each crossing, we write either 0 or 1, and if that crossing was a positive crossing, the 0 means this object, and a 1 means this object, whereas if it's a negative crossing, the roles are reversed. And now we assemble these 2 to the n different smoothings of our knot as vertices of a hypercube. And at each vertex of that hypercube, you have now a singular knot. I've told you what algebra to associate to that singular knot. And we're trying to build a chain complex. So to build a chain complex, what I have to do is I have to define the maps associated to edges. Now, an edge means that you've got 2 different singularizations of a knot which differ by either they differ in a single crossing. So either you're taking a singular point and you're smoothing it, or you're taking a smooth point and you're singularizing it. And associated with those 2 pictures, there are 2 different maps. This is what you might call an unzip homomorphism, because you're unzipping that singular crossing. And here, the associated map of rings is just the obvious one. It's a map of rings. You take 1 to 1. The point here is that here we're dividing out by more relations than over here. So there's just a natural map from here to here. And for the second picture, the story is slightly different. Rather, the map is induced by multiplication by UA minus UD with a T in front of it. So this is the zip homomorphism. So I've got this ring over here, I've got the ring over here. Multiplication by t times UA minus UD induces a map of modules, and therefore you have a well-defined map associated to each of these edges. And now it's not so hard. I've been working with Z2 coefficients. It's not so hard to show that each square commutes, so d squared equals 0. So you can take the homology groups of that chain complex, and you end up with not Floer homology. The invariant that I started out with at the beginning. And I'm done.
Does this provide a framework for telling you when the degree of the Alexander polynomial is related to the genus in some way?
Yes, I mean, so the point is that you have the genus, which is let me draw this picture. So from our point of view, we have some blob which computes which is the not Floer homology. When you take the Euler characteristic out here, that Euler characteristic might be 0, because you might have canceling pairs of z's. And then after a while, it stops having trivial Euler characteristic. And that's where the Alexander polynomial starts. So it gives you a way of thinking about when.
Yeah. So I know when the Alexander polynomial starts. I know when the genus, how to compute the genus. But is there a way of characterizing the knots for which those two things would be the same?
I don't know of an interesting way of rephrasing that characterization. It's only just the principle that the Euler characteristics are trivial. So I don't know.
Okay.
Any other questions?
Could you say something about how Combinatorial homology and this theory might fit together, some triply graded theory or something like that?
Well, what you'll notice if you think about Kovanov's theory is that Kovanov's relations are almost the same as these relations over here. They just have t equals 1. The only difference between this cube of resolutions picture and the one that you see in the Kovanov-Rosansky-Humphrey homology is that we divide out by larger relations. We divide out by these relations associated with larger sets. So it's already quite clear that the two theories they're very closely linked, but I don't yet have a concrete mathematical formulation of what the relationship has to be.
The G-symmetric power of the surface is sort of a precursor to the Jacobian. The surface had a complex structure.
Right.
Is that an accident, or
No.
the symplectic thing descends to something on the Jacobian, divided out by linear equivalence?
So the theory. Where to start? So it's easiest to talk about Hegardt-Floer homology in its original instance, which is where one works in the G-fold symmetric product to construct a three-manifold invariant. There, indeed, we're working with this G-fold symmetric product, which is birationally equivalent to the Jacobian, but it has spheres in it. So the holomorphic geometry is richer. And in fact, if you tried to do the same construction that I wanted to in the Jacobian, you would end up with simply computing the first homology of the three-manifold. You would not get an interesting three-manifold invariant. So it's kind of amazing that everything that's interesting has to do with the fact that there are those extra spheres in the G-fold symmetric product.
Well, let's thank the speaker again.